Welcome to the Intermediate Algebra Review of Number Systems. My name is Roy Simpson. I'm a professor of mathematics at Cosumnes River College in Sacramento, California. In this lecture, I'm going to just talk about number systems from a perspective where I'm not going to teach you. Instead, I'm just going to review some of these topics here. There are a couple of prerequisites, actually, not just this one. There's also elementary algebra. So you need to be able to be good with arithmetic and obviously have taken an elementary algebra course. In an elementary algebra course, you'd spend much more time going through this review topic, actually this topic in elementary algebra. Well, let's go ahead and step into this. We're going to talk about the container model for number systems, but first we're going to introduce our first set of numbers, our first group of objects. The set of natural numbers contains numbers of the form 1, 2, 3, and so on and so forth. These are known as the counting numbers. And because it's a set, we use set notation. That's the braces there. Just means it's a set of objects starting with the number 1, 2, 3, and the pattern continues. These ellipses mean that this pattern will continue. Maybe I should put AKA. These are the counting numbers, because obviously this is what we use to count. And also, they're called the natural numbers because they really are the numbers that we would make naturally. These are the numbers that we talk about in daily life. You talk about, I have a couple cell phones, or I have 3 sodas in the refrigerator, or something like that. But you rarely talk about having 0 objects. So that's why these are called the counting numbers, the natural numbers. And where it says the container model of number systems, this would be our smallest container. So that's what we have here, the smallest container. You can kind of think of it as a briefcase that holds the numbers 1, 2, 3, and so on and so forth. Those are the natural numbers. So let's move on to the next larger set of numbers, which are the whole numbers. Now the whole numbers, these are basically the numbers that start with 0 and then go 1, 2, 3. So it's not really much of a difference between the whole numbers and the natural numbers. They are only slightly different. They contain the number 0 as well as 1, 2, 3. And in fact, a lot of people write this as it's the set of objects being in this group, 0, unioned with the natural numbers. Notice the notation, by the way. I didn't note it last time, but that N with an extra little leg, that's the symbol we use for the set of natural numbers. This W with the extra leg is the symbol we use for the set of whole numbers. So the set of whole numbers contains the set of natural numbers. Also, it contains the number 0. And going along with the container model, I'll go ahead and draw a container around this. And you see that our container of whole numbers contains 0 and all the natural numbers, 1, 2, 3, and so on and so forth. So the whole numbers contain all the natural numbers. It's a container model for it. Now moving on to the next largest container, we'll look at the integers. And the set of integers is denoted with a capital Z with an extra bar on it. It's actually German for something I can never remember what it is. But this set of numbers, well, it has 0, it has 1, it has 2, it has 3, and so on and so forth. ... But it also goes in the other direction. It has -1, -2, and -3, all the way in the other direction. And of course, it's a set of objects, so I'm going to go ahead and put it inside the set braces here. And if you look at that set of objects, it really is basically saying that you have everything up to a -3, a -2, a -1, all the nice whole looking or natural looking negative numbers, unioned with the actual set of whole numbers. So this is the integers actually contains the set of whole numbers. So let me draw that on our model down here, our container model. Okay, so you see right here, the integers go all the way up to -3, -2, -1, and they contain 0 and 1, 2, 3. So again, just like one of those dolls, those Russian dolls, that you open up and there's another smaller Russian doll and so on and so forth on the inside, that's exactly what you have here for the these sets of numbers. Now we get to the more complex set of numbers, which is the rational numbers. The set of rational numbers is a little bit more difficult to deal with, and the key part of knowing what they are is this beginning of the word rational. It says ratio. It's really a set of numbers that's ratios of integers. So let me write that down. So we see we have the set of all ratios of integers where denominators are definitely not zero, okay, because you can't divide by zero. It is kind of an illegal operation. So these include, instead of actually writing this out in set format, I'm first going to give you an example. So let's look at like ratio of integers. So let's say a -1 over 7, or 13 over 8, or negative 54 over 1028. Now I understand since we know arithmetic that you want to reduce this fraction, you can, but the fact is, because it's a ratio of integers, this is a rational number. Now remember, the definition states that a rational number is a ratio of integers, so technically we probably couldn't say that this is a rational number. However, it might not initially look like a rational number, but we might be able to make it into a rational number if we do some magic to it. So for right now, point an arrow at that and saying it's not in the form to be called a rational number, but it is actually a rational number, but it's just not in the form that we would initially know. By the way, in mathematics, it's pretty improper to put decimals within fractions. So this right here is kind of a no-no. Most instructors would frown upon that. So please do not, in your course, put decimals within fractions. Even though we'll learn eventually that this is actually a rational number, it's just not a good idea to do that. Okay. Now, going back to the definition, we're going to go ahead and clean that definition up a little bit and make it more specific. And the specifics that I'm talking about is really just giving it a better format. So the set of rational numbers is a set of values of x such that x is equal to p over q, where p and q are both elements of the set of integers and q is non-zero. It's a fancy way of saying the same thing I just said. But all this notation, very important for you to get used to in intermediate algebra. So this is called set builder notation. So as an aside here, maybe I'll just define some of these things. Set builder notation. Set builder notation has the format, the set of objects, and then conditions. And it's red, that little brace right there says the set of, and then this just says values of x. That pipe there, the vertical pipe, is read as such that, and then in here, this is some condition that must be satisfied. Okay. So looking again back up here in our definition for rational numbers, we say that q, which is just a notation for the set of rational numbers, is equal to the set of values of x such that x is equal to p over q, where, by the way, p and q are integers and q is non-zero. And by the way, this means in the set of. There's a few little definitions you have to learn along the way in mathematics, and it's just because mathematicians are notoriously lazy, actually. And so what mathematicians tend to do is they try to decrease the amount of writing they have to do by using symbols. especially if things get repeated often. So if you're happening to say in the set of all the time, it's much easier just to write that little epsilon or e notation. Now, we have some examples of rational numbers here: negative 1/7, 13 over 8, negative 54 over 1028. But we haven't written the container model yet. So let's go ahead and write that container model. And it turns out that the container that has the rational numbers actually contains all these other numbers. And we haven't talked about it, but it's absolutely true. And here's the reason why. So the reason why is that, and I'll write it as an example. A number like, let's say negative 9 over 1, that's a ratio of integers. And actually, that ratio represents the number negative 9. So I guess negative 9, since it can be written as negative 9 over 1, negative 9 itself must be a rational number. Same thing as 0 over 10. That's a ratio of integers, and the denominator is not 0. But 0 over 10 is the same thing as 0. So I guess, since 0 can be written as a ratio of integers, 0 must be a rational number. 3 over 1 is another way to write the number 3. I guess, therefore, 3 must be a rational number. And just to show you that it doesn't always have to be over 1, 4 over 2 is another way to write the number 2. So I guess 2 must be a rational number. So let's see. We have 0, 2, 3, probably 1, 4, 5, 6, 7, 8, 9, 10. They're all rational numbers. So same thing with the negatives. So I guess all these sets of numbers here, the integers, the whole numbers, and the natural numbers, must also be rational numbers. Of course, we also have other special rational numbers like our negative 1/7 and stuff like that. But the problem here is there's no pattern. So you can't just list them all out and put an ellipse here because there's just there's no pattern to list out. So the dot 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 doesn't make sense there, okay? Because it's not listing everything out. There's some special things to note about rational numbers, and I'll note them in a second after we finish up our topic on the container model. We'll come back here and I'll mention another thing, because there's actually other representations of rational numbers. So I just want to make sure that we get that in here. But before we talk about those other representations, I want to talk about our last subset of numbers before we talk about the real numbers, and then we'll come back and talk about different representations of rational numbers. The irrational numbers. Now, the irrational numbers are a very, very special set of numbers, because irrational numbers are basically numbers that cannot be written as ratios of integers. Now, there's a key word here, numbers. A lot of people don't think about this, but I want to make sure that you see this. It turns out that, for example, 1 over 0, while that's a ratio of integers, it's not a number because you can't divide by 0. So that it would not be an irrational number because it's not even a number. So we're talking about things that we just can't write as fractions, and those are kind of hard to find when you're first doing a topic like this in mathematics. But you should have learned in your previous course what the irrational numbers are, and so let me give you some examples. So one kind of good example, very popular, is pi. Pi, there's no representation of pi as a ratio of integers. Pi is not equal to, contrary to the popular belief that it is not equal to 22 over 7. Okay, so some people think that it is. It's not. In fact, many people have tried to find in a very long time ago, tried to find a ratio of integers that would represent pi, and none exist. It's proven that pi has no rational representation. Another number that is irrational is the number e, a number that you will learn about in an intermediate algebra course, which it's roughly, only roughly, by the way, 2.71828, and so on and so forth. It goes on. There's no pattern to it, so except for the first several digits, I guess. Another one, another group, I guess, is like the square root of 2 or the square root of 3, the square root of 5. Notice I skipped the square root of 4 because the square root of 4 is actually just another picture meaning 2. The square root of 6, square root of 7, you get the picture, right? Dot, dot, dot. So anything that you try to take a square root of that is not a perfect square. All that stuff actually turns out to be irrational numbers as well. In fact, later on in mathematics, you might learn, or maybe you already have learned about, like the third roots of numbers. Like the third root of 9 is also irrational, or the fourth root of 17 is also irrational, or the 100th root of 28. That's irrational as well. So all these numbers are irrational numbers. Well, if you buy into all of that, which you probably should because that's just the definition, then the irrational numbers cannot contain all these other pictures because they're the antithesis of rational numbers. A number is either rational or it's irrational. In other words, a number, you can either write it as a ratio of integers or you can't. So if you can't, it's irrational. If you can, it's rational. So this is the first time in our container model that we'll be able to write a box that is not containing anything else. So this set of irrational numbers does not exist inside the set of rationals, nor does a set of rationals exist inside the set of irrationals. They're completely separate and apart from one another. Totally different groups of numbers. So, it leads sometimes to the question, astute students will ask this, well, it looks like you drew the set of irrational numbers to be a smaller box than the set of rational numbers. Does that mean that there's less or fewer irrational numbers than there are rational numbers? The answer to that question is very advanced, but, and there's no point in you knowing this, other than just kind of funness, there are actually technically more irrational numbers than there are rational numbers. It's not going to be very useful for you in intermediate algebra, but it's very, very interesting fact. Okay, and it's all about cardinality. If you want to read up wiki cardinality, then have fun with that. All right, so we have these two big groups of numbers now, the irrationals and the rationals, and it happens that the rationals contain all these other subgroups. Okay, let's go ahead and group these up and call this whole entire group of numbers, both the irrationals and the rationals, one special name. This group is known as the real numbers. The real numbers, we're back to kind of grouping things together very nicely. These are the set of irrational numbers glued to the set of rational numbers. So irrational numbers unioned with a set of rational numbers. The reason why I didn't use a letter for irrational numbers is because I can rarely remember it. I think it's an I, but I don't want to lie to you, and I'm too lazy to look it up. Okay, so that's, for now, all the numbers you need to know. There is actually another subset of numbers called the complex numbers. It's not actually a subset. It's a whole different group of numbers. Well, it's not even that, actually. It's a bigger container that contains this container. But for now, we're going to work in this world of real numbers. Let's go ahead and identify the number set, and in fact it should say set or sets, a given quantity belongs to, because some numbers will belong to several sets of numbers. For example, -3. Well, I happen to know that -3 is an integer. So it's a negative, some people like to call it a negative whole number. So it definitely belongs to the integers. But the integers belongs to another larger set called the rational numbers. Q for quotient, by the way. Okay, so it belongs to a set of integers, which belongs to a set of rational numbers. By the way, the set of rational numbers belongs to the set of reals. So if you remember way back in set theory, or I think we may have learned about this in junior high school, something like that, that if you want to say something's a subset of something else, you use this notation, like this is a subset of, so the word this is a subset of this and that. Okay. We have this set of words here. not drawing my braces nicely, but oh well. Anyway, this is a subset of this set of words. One of them being this. Okay, so if I want to use that subset notation, I could easily say, well, listen, that -3, it belongs to the set of integers. Oh, which is, by the way, belonging to the set of rational numbers, which, by the way, is still belonging to the set of real numbers. There you go. 2/5, that's definitely not a whole number or a natural number. It's not an integer, but it's definitely a ratio of integers. And of course, ratios of integers being rational numbers also belong to the set of real numbers. So both of these are true. Square root of 256, this is the tricky one because a lot of people might say that's irrational, but it turns out that the square root of 256 is actually 16. 256 is a perfect square, so I could easily take a square root and it becomes the number 16. And that number 16, well, that happens to be a natural number. Aha, but the natural numbers are a subset of the whole numbers. Aha, but the whole numbers are a subset of the integers. But wait, there's more. The integers are a subset of the rational numbers, which are a subset of the real numbers. So it belongs to all these sets of numbers: naturals, whole, integers, rationals, and reals. Square root of 24, I cannot easily take that square root, so that is going to be an irrational number. And I didn't give you a notation for that, so I'll just write irrational number. That's what it belongs to. But remember, the set of irrational numbers is still a subset of the real numbers. So it belongs to those two sets. And pi is the same. It's an irrational number, but it also belongs to the set of real numbers. All right, let me just finish that out. Boom. Okay. So each of these numbers belongs to at least two sets, and that's how all real numbers are going to be. Now, getting to this subtopic that I kind of warned you about earlier, representing fractions as decimals. It turns out that if you have a terminating decimal, that means a decimal that you can write on a piece of paper and get it finitely done, like 0.25, you're done, right? Then you have, that can be represented as a rational number. Same thing if you have a decimal that repeats. Now, when I teach this in a class, I will actually just say any decimal that has a repeating pattern is considered a rational number. So there it is, written as a theorem: any decimal with a repeating pattern is a rational number. So let's see why I didn't say anything about the terminating in that case. We'll start with the ones that actually look like they terminate, and then we'll move on to the repeating pattern ones. Like 0.25. I had mentioned that a moment ago, 0.25. That actually does have a repeating pattern, honestly. The pattern is a bunch of zeros. At the end of it, these zeros go on forever, right? So that's what I consider a repeating pattern. That definitely can be written as a rational number by this theorem, which we have not proven, but is true. Here's how you could do it. 0.25 is saying 25 hundredths, right? That's the hundredths place. So let's convert that to a fraction, 25 over 100. Oh, and I already see it right now, 25 over 100. I don't need to reduce that just to find out if it's a rational number. It's a rational number. It's a ratio of integers. There's a 25, there's a 100. Boom. So that implies that 0.25 belongs to the set of rational numbers. All right, so using that example as a basis, we could probably quickly see that any other number that has that pattern to it, like let's say a 13.2811, well, that is a repeating decimal as well. It's just there's a bunch of zeros repeating at the end of that, 13.2811, and then here goes the repetition. It goes on forever with a bunch of zeros. So I could write that as a fraction if I note that 13.2811 ends with the, well, let's see, that's the tens, the hundredths, the thousandths, the 10,000ths. 10,000ths. So that means that this can be written as 132,811 all over 10,000. Well, isn't that an integer on top and isn't that an integer on the bottom? Sure is. So that means that this number, 13.2811, definitely is a rational number. It's not a proof, these are justifications for right now. But the fact is if you have a terminating, if it has that pattern where it just ends with a bunch of zeros, easily can figure out that it is a rational number. As for the ones with the repeating pattern, not so easy to prove, but to justify we can still do kind of the same thing. Well, not the same thing at all, but a little more of a tricky way to do it, but it'll work. Now I want you to put on your thinking caps because we're going to do a little something that's a bit more advanced than what you might do in a classroom. But the fact is you can pause, rewind this. You can ask questions on the YouTube page to maybe get some clarification. And somebody might answer or I might answer. But the fact is this is a better way to approach mathematics. Try to be rigorous. Try to think. Not just digest what I tell you, but think about what I tell you. So here's an example. Take a look at 0.357, 357, 357, and so on and so forth. In other words, this pattern of 357s continue on forever. A better way of writing that, by the way, is 0.357 with a bar on top. That bar means that you copy and paste, 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 paste. Okay? Now, if I want to find the rational number representation of that, in other words, the two integers such that their ratio will equal that, I've got a little bit of work ahead of me. I mean, it's not going to be 357 over 1,000 because that wouldn't give me the repetitive 357. You could see this. In fact, let me bring up a calculator and show you. Here's a calculator right here. I think you can see the whole thing, maybe not the top, but if I did 357 over 1,000, you'll see that this is just 0.357. It's not the entire number. Okay. So, what do I do? I mean, if I can't write it as 357 over the 1,000 because the thousands place is right there. Well, let's go ahead and let n equal this 0.357. Now, normally you wouldn't have to do this because the fact is that you will, after this proof here, you'll be able to kind of believe what I'm telling you and be okay with it. But for right now, let's go through a rigorous proof. N equals 0.357, 357, 357. One thing I can do with that n is I can multiply, or with that equation, is I can multiply both sides of it by any number I want. And I'm going to multiply both sides of that equation by 1,000. And the reason why is that it'll allow me to move the decimal place on the right hand side. So let me go ahead and multiply the left hand side by 1,000 and the right hand side again by 1,000. And don't worry if for right now you're wondering what the heck is he doing? This looks too darn confusing. Okay, so the left hand side just becomes a regular old 1,000n. The right hand side, well, when you multiply a number by 10, the decimal moves over 1 to the right. If you multiply it by 100, it moves 2 over to the right. If you multiply the number by 1,000, it moves 3 over to the right. So we get 357 point. And then we have to start copying down the rest of the pattern that goes on. Well, the rest of the pattern is just 357, 357, 357. So it's this thing right here. All right. So I have 1,000n is equal to 357.357 on forever. What was n originally? What did we say that n was? I think we said that n originally was just 0.357 on forever. Okay. Well, here's a little interesting tidbit in mathematics. Sometimes it's useful if you have two equations, to subtract one from the other. So if I say, oh, you know, I have 1,000n is equal to 357.357 on forever, and I have n is equal to 0.357 on forever, maybe I could subtract everything on the left-hand side from each other and everything on the right-hand side from each other. In other words, 1,000n minus 1n, well, 1,000 minus 1 gives me 999 of those n's. But look what happens on the right-hand side. I have 357 point and some change. And from that, I'm going to subtract off, well, the change. It's like saying I have $357.35, and you say, okay, well, how about you lose 35 cents? Then all I should have is 357. So wait a second. N itself was equal to 0.357 on forever, right? But at the same time, I'm about to show you right now, when I divide both sides of this equation by 999, that N is actually also equal to 357 over 999. Don't believe me? Well, let's see what 357 over 999 is. 357 over 999. 0.357, 357, 357, and then the 4 is there because it rounded up the 3 and then the 5 and the 7. It rounded up that last part. So it is a 0.357 on forever. Interesting. So this number right here, because it's equal to a ratio of two integers, must be a rational number. It turns out that all of numbers with a repeating pattern, whether they end with zeros repeating or they just have a chunk of things repeating, those decimal numbers will also be rational numbers. Okay? And I used a calculator. You could also use long division to figure out what a rational number is, or what a ratio is, a fraction is, as a decimal. So if you want to. But that involves long division. That's arithmetic. So you could do that, and that's your choice. The final thing I want to talk about in this lecture, before I stop, is the axioms that build the entire set of mathematics that we use to this day. They're just 10 little axioms that allow us to do everything in mathematics, including almost create calculus. Now, I should note here, an axiom, some people feel as though axioms and theorems are the same thing. Axioms are sort of like theorems, sort of, okay? Sort of like, that's the mathy language right there, roughly equal to a theorem. Except that we don't prove these, these are universally accepted truths. So I'll write that down, universally accepted truths. There are just some things in life that you go, listen, it's true because, well, I don't know, it just is true. Can't you believe me or something like that? I don't know. It's one of those things that that we all just accept as being true. And so there are 10 of these things in mathematics in general. And so we'll go ahead and write them down here. So here goes our generally accepted truths. First of all, we'll just say let A, B, and C all be real numbers. So be in the set of real numbers. Okay, I'm just kind of chicken scratching that out. No offense to any chickens in the audience. So the associative properties of addition and multiplication, those are two properties. Addition, associative property of addition says that if I have two things, well, let's say three things, actually adding A plus B plus C, we will assume that it is true that I could first add A plus B. Remember PEMDAS, you add what's in parentheses first. So we could first add A and B and then add C, or we could have associated it differently and added B and C first. So notice the associations are different. Here I associate A and B, I can add those first, then add C. The axiom, what we accept as universally true, we all just kind of go, duh, it's true because it's true, is that you could have first added B and C and then added A. Okay. Multiplication has a similar property. You could multiply A and B first and then multiply that to C, or you can multiply B and C first and multiply that to A. Again, just associating the numbers differently. Commutative properties, well, you commute to work. It's just like moving. Commuting is moving. So these are like the moving properties of addition and multiplication. In other words, if I'm going to add a plus b, I could have added it in the other order, b plus a. We assume that we can do that. Same thing with multiplication. A times b, we assume that's the same thing as b times a. Now, some people say, well, isn't that a lot to assume? Most students would just say, yeah, of course, that's right. I know that's true. 3 plus 4 is the same as 4 plus 3. 3 times 4 is the same as 4 times 3. But the astute student, and I always am a fan of the student who thinks, would ask, well, is this always true? I mean, is it always true that we could do that? Not only is it always true, but does it have to be? What if it wasn't? Turns out there are some systems out there, some number systems that exist where this isn't true. But if it's not true, then math doesn't work very well with them. Okay, there's a special type of this is a very special type of number system that it satisfies all these properties, and if it does, if we assume all these properties hold, then everything that we know in the world works out nicely. But if you assume that one of the properties doesn't hold, then things go strange. And it's pretty interesting. You can make some very fun number systems. All right. Additive and multiplicative identities. Well, we have to assume that there's some number in the set of real numbers that we can add to A to get us back to A. And that number we're going to go ahead and call 0. Okay, so that's our additive identity, is that A plus that number 0 will just return A. And along the same lines, we have something that we're going to multiply against A to get back A, and in our number system, we will call that the number 1. A times 1 will equal A. And again, that's one of those things that we just go, well, duh, yeah, that's true, right? Additive and multiplicative inverses. Well, if I have A and I want to add it to a number to come out to be, to come out to be 0, what number can I add it to? Well, we assume you can add it to the opposite of A. A plus the opposite of A, we are assuming will be 0. Again, one of those situations where most people go, yeah, of course. Same thing, if you want to multiply A by a number to become 1, notice multiplication is all centered around 1, and addition is all centered around 0. What would we multiply A by? Well, it'd be 1 over A. That is the multiplicative inverse. Okay? Multiplicative opposite, you could say. Finally, the distributive properties, there's actually 2 of them. A times the quantity B plus C, we will assume that turns into AB plus AC. The other one is quantity A plus B times C will turn into AC plus BC. It's just distributing. You can either distribute to the right or you can distribute to the left. Okay. Just to let you know, those are some background theory things in mathematics, but I think it's very important to be able to know that stuff and know that it exists. So from this point forward, when somebody says, hey, yeah, 3 plus 4 is the same as 4 plus 3, you don't have to go, no, it's not. It is. It is, because we assume in our number system it will be. All right, that's enough for this lecture.